All right, the first 200 milliseconds of HTTPS. This is going to be a really awesome talk, at least for me. I don't know how it will be for you. Today I will talk about something we use each and every day. Obvious question, who is actually using HTTPS? Who has ever been to an HTTPS website? Is there anyone who didn't raise their hands? No? Okay. So at least we all use it, but who knows actually what it is? How does it work? Anyone? Well, one. Okay, so today I'm going to explain a little bit about the basics of HTTPS. It can be a little dry. I hope not too dry. If so, then please raise your hand and I will just, try to make it a little bit less dry. I will, however, talk a little bit more about some of the backgrounds which you can use as well. So first of all, I want to start with myself. I like to talk about myself, but I leave it very, very quickly. My name is Jeff Thijssen. I do lots of things. If you want to contact me, you can... All right. If you want to contact me, you can find it here as well. So today I'm going to start with showing you what's happening in the first 200 milliseconds of an HTTP connection. That is the most important part during the whole connection. That's normally known as the handshake, TLS handshake. However, I will try to give you some tips and hints on how to hardening your setup. So if you have a website that actually uses HTTPS, hopefully you can use some of the tips I will show you to even make it more secure than it already is. Maybe it isn't, but we'll figure out. And I will try to give you some insights on new and upcoming technologies. I was approached by somebody just recently who wants to know a little bit more about a feature that's going on right now. It's called PFS. I will talk about it at the end of the talk as well. So I will show you what's going on right now, especially with all the NSA stuff and the PRISM stuff we all know about right now. And I will try to show you some things that you probably didn't know. Maybe you did, maybe you didn't. So first of all, this talk is inspired by a blog post from Jeff Moser. And that's a really awesome guy who actually just got an HTTPS connection and just blocked about every single byte that's happening. Why is it there? Where is it for? And what does it do? So if you're interested about this talk, definitely take a look at this URL because it will be even more in depth on what's going on. So I said before, HTTPS, what is it? A lot of people think that HTTPS is a protocol, which it isn't. Just like TCP/IP is not a protocol, it's a combination. HTTPS is exactly the same thing because it's HTTP over TLS. So there are actually two protocols involved. The HTTP part, we all know, and the TLS part, which is the transport layer security, which is the stuff we actually talk about today. So when we talk about the first 200 milliseconds of HTTPS, what I actually mean is the first 200 milliseconds of TLS. Before I can explain what TLS is, I want to show you a really short and scary history about where it comes from, namely SSL. And I think you all heard the term SSL, right? Okay. A long, long, long time ago, maybe even people weren't born, 1994. Anyone younger than that? Raise your hand. It's possible. There was SSL 1.0 that was created by Netscape. We all maybe know Netscape. That is vaporware. It never has been released. Considering what comes next, that is actually a good thing because that would be really, really shitty code. A year later came SSL 2.0, codename Not So Secure Socket Layer, which exactly says what it is on the tin because it isn't really that secure. A little bit later, in 1996, there came SSL 3.0, and hooray, something stable, something releasable. So this is what they did, SSL 3.0, and this is also the time that the internet became booming. People started to upload pictures of cats. Twitter wasn't there yet, but we had ICQ and stuff like that. But also e-commerce came up. So people wanted to be more secure. People did their work with Telnet and FTP and decided that's not really so secure. Let's try SSH and let's try secure FTP. The same thing happened with our web browsing. So we saw more and more secure sites on HTTPS. So a little bit later on in 1999, that was, you know, the height of the boom, well, close to. A group of people took over, and a group of people called the IETF, the Internet, what's it called, the Internet? Yeah, it's like the people want to regulate everything, but they have absolutely no power. It's like the Dutch police. Nobody takes them seriously. I'm sorry, I like bashing my own. But because they took over, they said, no, we don't call it SSL anymore, we call it TLS. And we call it TLS 1.0. But actually, this was SSL 3.1, because they're really, really similar to SSL 3.0. There was only a few minor things that has been changed. So to make things confusing, because TLS isn't confusing in the first place, you have TLS 1.0, which is the same as SSL 3.1. It will be obvious why this is an issue. Issue. And after 1999, there's a whole lot of nothing. Because in 2006 came TLS 1.1, which isn't really that different from TLS 1.0, but it has changed some minor things that were really complex in SSL 3.1 or TLS 1.0 has been fixed into something easier, but on the whole, there wasn't really much changed. Then again, 3 years of nothing and 2 years nothing, and in 2008 came TLS 1.2, which is the latest version we have. So the latest version is now 3.5 years old. So obviously everybody is on TLS 1.2 right now, right? This is the scary part, because these are the current versions that are really right now in live on the internet from November 2003. It's taken from trustworthyinternet.org, so that must be true. But I believe them. Maybe the numbers are slightly off, but this is close. I showed you that SSL 2.0 is really crap and you shouldn't use it. Still, 25% of all the websites on the internet accept SSL 2.0. So they accept a not so secure connection between you and your browser, while your browser still say, hey, there's a secure line between me and the server, which really isn't if it's on SSL 2.0. The SSL 3.0 and the TLS 1.0, they have market domination. Now, if this was your company, I would be really happy. But these are still in use, and it doesn't change right now. TLS 1.1 and 1.2, 3 years and 5 years old, still pretty much no adaptation. So that's strange, right? That's something that's really scary. So this one is really borked. Don't use this one. You can use it, but really upgrade. It's like the PHP 5.3. People use it over and over, but try to upgrade. And these are okay. So these are like the PHP 5.4 and 5.5. So if you got a new site, make sure it supports TLS 1.2. You can't really, I will explain later on. So this is a talk about TLS 1.2, the latest version. So there's not much difference with the old versions, but I will talk about TLS 1.2. Of course, you all did your homework, and you all read RFC 5246, right? Yes? Okay, page 6, line 5, the first word. Correct? Excellent. Now, this is the RFC that actually defines what TLS is. If you have nothing to do on a Saturday or Sunday evening, just read it. Maybe on your work, I don't care. Just read the RFC, it's really nice. What TLS is a binary protocol, so it's not like HTTPS. You can just look at the line, what's going on, and just see, oh, there's a GET request, and there's a response, and so it's binary. You can't really just telnet or capture it and see what's going on. However, you can with something called OpenSSL, which is there, which makes it easier, but it's still a binary protocol. It's got different algorithms and really difficult algorithms depending on the version you're going to use, and different handshakes. So they're all pretty similar, but still it changes a little. But one of the cool things is it's easy extendable. That's actually being used right now a lot. So you can actually add your own, literally, plugins into TLS. That's actually happened for something called SNI, which I will show you later on as well. So it's a really cool framework that works, but you can plug in your own custom stuff as well if browsers and servers support it. So today I'm going to talk about the first 200 milliseconds, which is the handshake, which is a client and a server, and a client does stuff, the server does stuff, the client does stuff again, the server does stuff again, and then we get to the HTTP part where you have a secure connection where you can actually communicate. So this is like the TLS part, this one, and over here you get the HTTP part, and combined it's called HTTPS. Okay, to make it not so dry as going over every byte, I will do some live Wiresharking. Will be fun. Well, it's not live, it's semi-live. I already took the capture, so I just display it to you here on my computer to see what's going on. And I will just start with the beginning. So I will start with a client, your browser, and the browser just connects to a website, HTTPS, github.com or whatever, and it wants to open a connection. So the first thing it's going to do is send a client hello. So what's happening here, and I will do some Wiresharking. And this is going to be fun because I can't see it here, so I have to look this way. Can everybody read this? Yes. All right. Who knows about Wireshark? Okay, different question. Who doesn't know about Wireshark? So everybody else? Okay, so Wireshark is really a cool application that can just sniff on your network interfaces. So I just sniffed my Wi-Fi interface to see what's going on between my computer and, in this case, the computer of somewhere on the internet. And there's some packages going from my computer to the server and the server to my computer. And the first package is the client hello. Now, you can see here, if you know a little bit about TCP/IP, that this is like the IP part, this is the TCP part, and here's the TLS part. They're all stacked together. So I'm going to talk about this thing. And this is just a record layer. So TLS are just multiple records on top of each other. So you can use multiple records. And the first record that's going to be sent is something called client hello. So the client announces itself to the server. There's a lot of things going on. As you see here, it says that it's a certain version, TLS 1.0. And you see here, 0301, TLS 3.1. This is where the confusion can come in. Now, what's happening in the client hello? There's a lot of things here. And the first thing you're going to see is that inside that record, I'm going to talk TLS 1.2. So there's a different version inside that package. It's TLS 1.3 and codename SSL 3.3, so the 0303. Now, first thing what a browser does is send a random number. And that random number consists of the timestamp. That's the current timestamp, so I did this at 7:08, and some random bytes. Now, who of you has ever generated random bytes? Probably everybody who has used rand or something like that. However, what a lot of people don't know, and I'm going back to my slides, is that generating randomness is really, really, really hard. Harder than most people think. Because what's happening is a computer cannot generate random stuff. A computer is predetermined to do things that it's ordered to. So if you say, I want to get a random number, it has an algorithm that gives you a number that seems random, but actually it isn't random. It's a pre-generated number. So that's why it's called pseudo-random generators. So it looks random, but actually it is a difficult algorithm. So to get something random, you need entropy. Entropy is another word for uncertainty. There needs to be uncertainty, and the more uncertainty that you can feed into your algorithm, the more random the number is. Anyone know of a entropy source. That's very random. That's a good entropy. But yeah. How about time? Well, it's a good thing that people say, no, it's not an entropy source, because time isn't really a good entropy source. Because time, we know time. I know exactly what the time is in about 1 hour from now. I showed you in the Wireshark that I actually sent the time of the server to the client, or the client sends it to the server. So we already know what time it is on the server. So in this case, time is not really a random thing, and it's not really a good entropy source. PHP, I'm going to do PHP bashing. I really love that. PHP is really bad when it comes to entropy, because most of its entropy sources is the time. If you go and look into the PHP sources, you can find it pretty much uses time all the time. All different kinds of way, but in the end, it's pretty much always the time. Anyone did this? Probably, huh? Right, so that's the most common. If you go to any website that says, I need something random, okay, just do asround microtime, and then you get random values. Yeah, you can do that, but if you do this for creating salts for your password, or actually generate password, or generate activation keys, or activate password, I don't remember my password, but here's your secret key that you can use. If you do this kind of things and then generate a random number through one of these, you're going to be pretty much screwed with a capital screw, because it's really easy to figure out what it is. Actually, there are applications right now that can just figure out what kind of random seed you actually used by just looking at a few random numbers from your application. So it's that bad. If you're going to use random numbers for anything else than just say, do we need to do a random black background or white background? If you do something more complex than that, use one of the following things. There's something called OpenSSL pseudo-random bytes. It's a long name, I know, but it actually generates cryptographically strong enough random numbers that you can use. So for cryptography, that would be pretty okay. You can also read directly from, if you're on Linux or OS X, you can use /dev/random or /urandom. That actually is a file on your operating system that gets fed by all kinds of different sources, like the traffic from your Ethernet connections, the wiggling of your mouse, touching the keyboard, all that kind of stuff gets fed in that file, and that creates more entropy, so more randomness, so better for cryptography use. You can also use a hardware number generator, which could be like a simple USB stick that actually use white noise or stuff like that from, radiation, things like that. You can do something like that. They told me last week, and I didn't know that some processors, like the Intel, actually have a number generator on board that does stuff like this. So there's a, it's not good? Yes, no? Yes, it's not good. Yes, it's not good, okay. Well, screw it, don't use it. I have to figure out why, but I'll believe him. There's actually a really cool thing. It's called A Million Random Digits. It's actually a book. It's a book created in 1940 or 1950. It's just a book with 1 million random digits. You can actually buy it on Amazon. You can look it up. You can actually see what's inside. Read the comments on that book, because it's hilarious. If you have not enough on 1 million random digits, the book, there's a sequel, another 1 million digits or something. So you can do that. It serves a purpose, because back in the 1940s and 50s, they actually used that book to calibrate random number generations on that book, because they knew that the numbers in that book were cryptography strong, so they can actually use that as a measure point to see if their algorithms are correct, yes or no. Not really practical, I think, to just use a book as an entropy source, but this one is really cool. There is a really cool library called RandomLib from Maxwell, Anthony Ferreira, and it's a simple system that you can use, and you can say, okay, I want a weak number, a medium number, or a strong random number. And if you get a strong random number, it takes a long time to generate. If you want a weak random number, it's easy to generate, but obviously it's weaker. So you can actually see what's going on. You can actually see if I don't need a really weak or a really strong number here, so I use a weaker one, so it will be faster. So you can actually use that library for that to, you know, take care of all the issues for that. So really take a look at that before you start using random, microtime, and stuff like that. All right, back to the Wiresharking. So generating a random number isn't really that easy as it looks here. One of the most important things here is something called cipher suites. And you see that my browser sends 18 different cipher suites with all kinds of really complex codes. And this is something that is pretty much the heart of your whole TLS, the whole security. I'm going to show you what actually these things mean, if I can get back to my browser. Oh, hang on. I will show you that later. But I will show you the extensions here as well. I told you that TLS is extendable with so-called extensions or plugins. And one of the plugins is called server name. And it's actually server name indication, or SNI. Does anyone know what it is? Just one? Just two? Okay. Do you know virtual hosting? Yeah? You have multiple hosts on one IP. Yeah? People say you can't do that with HTTPS because you can only have one HTTPS on one IP. SNI makes it possible to have multiple hosts on one IP through HTTPS. So it's a really cool thing to have. And it's just an extension, so it's not in the TLS specifications, but it's actually extension in a separate RFC. And it just says here that in this case, the client sends it to an IP, but it actually wants the server Microsoft.com. There's a reason I'm using Microsoft.com. I'm not a big fan of it, but I will show you later on why I use this one. So this is like the multi virtual hosting of HTTPS. So it's really cool. However, pretty much every decent browser and server supports it. So not only the server must support it, but the browser must support it as well. It is not supported for IE6, Windows XP, BlackBerry, Android 2.6, or 2. Whatever. So not a problem. There are some ways to get around that, but in this day and age, if you need something that needs to be run on IE6, the least of your problem is getting your site on HTTPS, I think. So if you're going to use it, you can use SNI without any problems. It's really easy to configure on your web server as well, but at least you don't need 10 IPs for 10 different websites. So I showed you the ciphers before, and you get something like this, right? There was a whole list of different pretty strange numbers. So I'll just split them up. You can skip the TLS and the width. They're just placeholders. The most important thing is these ones. This one, that's a pair. This one, and this one, that's a pair. And this one. So the first thing here is used for exchanging key information. I will show you later on what we mean by that. The second pair is used for authenticating our key information. There are some protocols or some cipher suites that actually have it together, so you have only one thing without an underscore. But that's for exchanging keys. The other part, this one, is the actual cipher we're going to use. So that's the actual, that says, okay, we're going to communicate, if everything goes okay, through AES 128 in this case. Does anyone have ever used AES? Yeah? It's a symmetrical cipher. It's a really quick way to communicate securely, but two sides need the same key. So that's a problem if you're going to use it, because you need some way to get one key over to the other side. That's going to be used in the key information. So AES is going to be used for the communication. We're going to use AES 128, so 128 bits of blocks. And this is a block cipher. It's not really important right now. And SHA-265, that's used for message authentication. So every time we send something from the server to the client or the client to the server, we send a signature with it. That's gonna say, okay, whatever I told you here in this block is signed off by me, and you can validate if it's not tampered with, and if I'm the actual person that actually has sent it. That also means that you can't replay it. So if I'm really an evildoer and I want to say, okay, I know if I send this package from, I captured this package from the client and I will send it over to the server an hour later and then I will get $100 million. No, it doesn't matter if that's the case. You can't do that because it knows that you can't send that package twice. So that's what's happening with the message authentication. So it's a really important thing, and that's automatically, increases the security of your HTTPS connection. So this is pretty much the same thing, but here we only use RSA. There are really cool cipher suites. I don't go into detail how they work because that's going to be way too complicated. But there's a really cool cipher called this. This actually exists, and your web server can support it. It will not do it out of the box. But what do you reckon this will do if I'm going to use this one? It will not do nothing.
Handshake, but not encrypt.
Yeah, exactly. It will do a handshake, but it will not encrypt any data. So you can actually use it for debugging purposes to see if your handshake is working or stuff like that. So if you are a client and you want to do bad stuff, you can actually tell the server we're going to use TLS nil with nil, nil with nil nil. If your server is really badly configured, you can actually have a secure connection, but without any security at all. So don't rely on just, hey, my browser is green, so everything will be fine. Because in this case, things won't be that fine. However, you have to do really strange stuff to get this working. I just showed you that the client sends a list of 18 different ciphers. Every browser sends their own pack of ciphers, but it's actually the server that decides on which one we're going to use. So the client just provides options. So this is the option I like the best, I put it on top. This one I like the second best, put it on the second place. And on the bottom, I have something, well, if you don't really have anything, then just use that one. But ultimately, the server decides on which cipher, so which encryption we're going to use. So you can't say per definition, if you have a connection, that, oh, that's a great connection because I know it's encrypted with a certain cipher. You don't know. It's not your call. It's a call between the server and the browser. So even if you're on the same web server, if you use Saffire, you can have a different encryption, even a weaker encryption, than you have with your Chrome browser, for instance, or your Opera browser. Okay? Anyone knew that? Yes, no, okay, sort of, kinda, okay, cool. This is why you should always configure your ciphers on your web server. How? It's easy, just take one of these and you're pretty much set. It's not really that difficult, but you can see here what's going on. But pretty much I'm going to tell, if you are using Apache web server, that you're going to use all the protocols except SSL version 2, which is a good thing that you don't use it, but I don't use version 3 as well. So only TLS 1.0, 1.1, and 1.2 will be used. The same here, but a different way it is written. The cipher suites are actually the cipher suites that I'm going to use as a server. So if the client says, okay, I support this one, AED, CDH, whatever, then the server says, okay, we're going to use that one. If you don't have one, we're going to check if you have this one. If you don't have that one, we're going to check if we use that one. All the way down to something called RC4. If RC4 is something that everybody pretty much can work with, so that's our default fallback. It's not really secure. It's going to be less and less secure in the next couple of years. It will be supported for the next couple of years. So don't use that unless you're absolutely certain that your browser don't support any of the others. So it will be always on last. And even, I know even some sites that don't even support RC4 anymore. They just say, okay, I'd rather not communicate with you than do really bad communication or bad security on communication. So that's something you can figure out. Pretty much, if you copy-paste this on your web server, that will be fine. Just read the docs. I won't be held responsible, but that's pretty okay. You can find out if it works, yes or no, by a really cool website, sslabs.com/SSL test. You can just punch in your website, and it will show you exactly how your HTTPS is functioning. I did this talk for the first time last week, and they asked me, okay, so how is the site for knoxlogic.com, my company? And I said, yeah, I don't really have SSL on my web server. So that was a bit embarrassing. So I just changed that this week, and I put everything on pretty much as a base what you saw before. I typed that, and it took me like 10 minutes to get an A rating with pretty much the highest standard possible. This is pretty much what you expect from your bank website, from YouTube, Google, stuff like that. You probably have this grade A security. If you have anything less, please reconfigure your browser so you can really figure it out and test your own company or whatever site on this one as well. It doesn't say everything, but it gives you a good idea on how it works. Okay, so let's get that going. So pretty much everything that the client needs to do has been done. Most important things: send a list of ciphers, send an SNI that says, okay, this is the server I need to communicate with, and get a random number over to the server. Always the same, huh? Always the same. So that's the client sending to the server, and now the server has to do some work as well. So now we're going to do the server. And here is where more fun comes. Oh, hang on. We get the Wireshark again. Yeah, so that's the client package. And now you will see there's a server package coming back. And the server package has here some other stuff as well. So again, you see there's a handshake message, TLS 1.0. And you see that the server hello uses response back in TLS 1.0. So Microsoft.com uses TLS 1.0 in this case. It doesn't say it can still be TLS 1.2, but in this case, this is a 1.0 package, so it talks as if it's 1.0. You see again that it sends random bytes again. So now client has random bytes given to the server, and the server has given random bytes to the client. That will be really important. And you see a cipher suite. And you see that it actually it just picked one cipher suite. Yeah? In this case, TLS RSA with RC4 128 MD5. I told you before, please don't use RC4. This is the reason why I used Microsoft, because I knew for a fact that they would use something like this, and I was right. To be honest, I used Google and GitHub.com before this, and they just changed it recently. And I mean, from January 1st or something, they changed it to a better encryption. So last year, they were still using that as well, but it has other reasons. But this is a cipher suite that actually Microsoft uses, but I showed you before that we send out a list of all cipher suites we want, with the highest one is our most preferred one. So if we're going to look down, we see here, this is the one Microsoft actually got. They said, okay, that's fine that you support all these really cool encryptions. We're going to use pretty much the last one, rock bottom. I'm not a big Microsoft fan by now, but you already guessed it. It got different reasons, because the higher ones will be more performant. You need more computation power to get that. So it makes sense on high traffic sites to actually see what kind of ciphers you're going to support because of efficiency and speed. So, hang on. So this is why they use TLS RSA with RC4. So we go back to the server hello, and that's pretty much what we did here in the handshake package. And there's a next package called certificates. And it sends here 4 different certificates. Who has generated an SSL certificate in their life? Yeah, pretty much everybody did it. Pretty much by, okay, Google how to create a SSL certificate, and then you see all kinds of open SSL commands, and you just type them, and it works, and you send it off, and have no idea what just happened, right? Okay, I'm not going to explain what you did, because it will take too long. However, I will explain what it actually is. So, these certificates are the things that make your bar green. Not so much green, but locked. It can be used for green as well, but this is the most important thing that will actually say to a site, this is secure. The green bar does not really say, oh, you have a secure connection because the cipher you're going to use, the cipher suite is really good. No, it's going to say, the certificate is okay. Everything is okay, honky-dory, with the certificate. So that's something really different. You know you're going to talk with, in this case, what is it? Online Trust Alliance. But it doesn't say if you are securely connecting with them. It just say, we know for a fact that it's OT Online Trust Alliance. So there's a difference. The padlock doesn't mean secure, it means we know for sure that it's them. So what's an SSL certificate? An SSL certificate is not an SSL certificate. Because actually the best name for that is an X509 certificate. Because SSL, we already showed you, it's an old name. It should be called TLS certificate if you want to do it correctly. But actually it's an X509 certificate. It's not automatically secure, because that's something that our cipher suites decide. It's also not automatically trustworthy, because there's still a lot of things that can go wrong on certificates. It's also not in a way better than self-signed certificates. I still hear people saying, oh, you should not use self-signed certificates because they're not so secure as the one from VeriSign. That's complete BS. They're absolutely the same security. And they're cheap, absolutely not. But we already know that. You can get cheap certificates, and to be honest, they're just as great as the more expensive ones. So what an SSL certificate is, it's the best way, but not the perfect way, to prove our authenticity. We can prove that I'm talking to my bank. I can prove that I'm talking to Google. That is what an SSL certificate is for. It's a way to bootstrap our encrypted communication. So we have the cipher suites, but we need to do some more stuff, I will explain later on. And we need our certificates or data inside the certificate for that as well. What it also is, it's misleading. Because if you're going to take a look at VeriSign or any company that sells SSL certificates, anyone around here that is in the business of selling SSL certificates? Oh, trust me, you don't want to raise your hand now. Okay, that's complete marketing BS, what you say there. Really. They have insurance that absolutely makes no sense. They say, oh, we support 265-bit encryptions. It's not your task. It's the cipher suite's task. And you're not part of it. So it's ridiculous. So if you're gonna need a certificate, unless you have really good reasons, get the cheapest one, really. Yes? That's the thing. I will explain later on why you would buy it instead of self-sign it. So it's misleading, and actually it is too expensive. It's really too expensive, but I understand it because some of the root authorities, I will talk later about, they have to spend so much time and money on auditing and security and making sure that everything is really, really safe. So there's an X509 certificate, and when you create one, you have to do stuff like, okay, I have to set in what kind of URL I'm going to use. I have to type in the name of my company and where I live and stuff like that. So there's all kinds of owner information. For who is this? There's also some domain information for who is this certificate valid for. And you have also expiry info. This certificate is valid between 2013 and 2014, so you can't use it in 2015. But it's really easy, if you know a little bit about it, to change the 4 into a 5, and then the certificate is valid for another year, right? Unfortunately, it doesn't work that way, because a certificate is signed. And the signing means that somebody else said, okay, this is the certificate, and I'm going to give my seal of approval, and if anything changes in the certificate, I can actually see that, I can detect that. So you can't tamper with it, because you can't change the signature, just like a normal signature. So what actually happens here is that you have a certificate for your domain.com, and that is signed by somebody. And that somebody is normally an intermediate CA. And that intermediate CA is just another certificate. So you get two certificates. And you can check this certificate to see if it's valid by comparing the information with this certificate. It's too complex to tell you how it actually works. I have another talk for that. But now we have the same problem because we have another certificate. Can't that be changed? Well, yes, because it's another certificate. So we have something else called a root CA, and that root CA is actually also signed by, the intermediate CA is signed by the root CA. But do we have another problem? Yes, because we can change this as well. It doesn't matter how long we make the link, there's always a certificate at the end that we could change, theoretically. But what's happening here is when we have a root CA, we trust them. We just say, okay, if you're going to have something like a root certificate, we trust it. We don't care how it looks like, we automatically trust it. Implied trust, it's called. There's a $ here. It's not for a very bad reason, because there's a lot of money involved. These are the so-called root certificate authorities, like VeriSign, like DigiCert, like DigiNotar. I think you all... Right. They're actually built into your browser. The certificates are inside your browser or your operating system as well, and you automatically trust them. So if you have a certificate that is signed by a root CA, your browser says, okay, I will accept it. I will not check verification, I will just accept it. So obviously you don't want them too much around in your system, right? You just want maybe a few and that's it, because I don't want to get the whole world. I don't trust the whole world. I checked it on Mozilla, NSS, which is like a security modules from Mozilla, and I just counted with this command how many root certificates in there. Any guesses how much I found? More than 10? 1,000. Oh no, that's... Oh man, if there were 1,000 certificates there, I would just unplug my system and just, you know, do something else with my life. No, 174. So there are 174 companies in the world that makes certificates that I automatically trust. And the only thing they do is in the business of selling as much certificates or signing as much certificates. So nothing will go wrong, right? So we all trusting a lot of different companies that we don't know and want to make money on selling stuff. So yeah, this is why you can't always trust the authenticity of your certificates, because I don't know what somebody else signed. Anyway, this is pretty much what the server sends back. So it sends back the certificates, and I can check with all the chains and to see how it works. And in the end, I can say, okay, this certificate from Microsoft.com is actually signed by somebody who trusts Microsoft.com, so I will trust it as well. So I give you a closed padlock, and if it's an EV certificate, an extended validity certificate, I will give you a green address bar, and that's it. Everybody's happy because now we're secure. That is what happened here. One of the things that not everybody knows is that when you have an SSL, an HTTPS connection, that when you have a server, you have to say, okay, this is me to the client, right? You send out certificates. But a server can ask the same thing for clients as well. It theoretically could ask a browser, okay, I just proven who I am, prove who you are. Now, obviously, for browsers, this doesn't really make sense. But if you have APIs that works on HTTPS, and you have a server-to-server communication, you can actually, have two certificates on both sides, and just say, okay, I want to prove who you are. I want to know who I'm talking with before we start our secure communication. So the server can ask that as well. Normally on browsers it doesn't happen, but you can do that as well. Okay, so this is where the server has done, and now we're back to the client. So all this talking took me 100 milliseconds. So we're halfway. Okay, again, the Wiresharking. No, that's not the Wireshark. Yeah, it's the Wireshark, but this one. So this is what we did, the server hello, and now we get something really important, and this is called the client key exchange. This is the most important step on bootstrapping our security, because what's happening here is that the server, in this case, sent over something called an encrypted pre-master. Now, I showed you before that Microsoft uses TLS, RSA, something, 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 right? It means it's going to use RSA for exchanging and authenticating key information. And that's exactly what this does. So it sends over an encrypted pre-master secret from the RSA to the server. So the client sends it to the server. And this is encrypted. And the only one who can decrypt it is the server. Everybody can see this, because I just Wiresharked it, so I've proven to you that everybody can see it. But nobody can do anything with it except the server on Microsoft.com, because they need a key, and that key is only there. So it's a really important key, because if they lose their key, everybody can decode things from Microsoft.com. So this is a really important number. And what happened, and when we have this number, we're going to do something called generating secrets. And I've got code in PHP that does this for you. It's really nice, but bear with me. I've got 3 different sources. So I've got the pre-master secret, I've got the client random number, and I got the server random number, right? Those are the 3 numbers. Those numbers create something called a master secret. The only thing a master secret does is getting the same things. So the server random and the client random, they are switched on in this case. And it creates something called a key buffer. It's too complex on how the algorithms work. But from that key buffer, we're going to split it into 6 different keys. A client MAC key, a client key, a client IV, a server MAC key, a server key, and server IV. So the MAC is used for verifying if the communication between the client and the server is actually valid. So we can validate that information. The key is the important thing, because the key is going to be used for encrypting and decrypting information between the server and the client. The IV is sometimes used, depends on the cipher suite. You sometimes need an IV, it's not really important right now. But you see, we do the same thing for the server. So what happens here is that when you do communication between the server and the client, that actually uses a different key than communication between the client and the server. So if you, for whatever reason, get hold of a client key, you can only decrypt something from the client to the server, but not from the server to the client. That's still, that's still encrypted. So that's like another fail-safe that, well, okay, you encrypt it, very good, but at least you get half of stuff. That could be really cool. So that's how it works. So you got 6 different numbers that are really, really important. That's all generated from these 3 sources. Okay. That's pretty much what happens on the client key exchange. And then we go do something called a change cipher spec protocol, or change cipher spec, that tells the client to the server, okay, every communication I do from now on, after this package, will be encrypted. So that is the last package you normally can see if you're going to snoop an HTTPS connection. And that actually works, because this is the second package you have to send, but it doesn't see what's inside. Wireshark can only tell me it's an encrypted package, but I have no idea what's inside, because that's already encrypted. And this is something that even, because I'm snooping the communication, I can't read it as Wireshark. So if you are snooping this communication, you can't see it as well. We only know there's something in there, but it's encrypted. So this is where it already starts to work. The same thing happens from the server on. So in this case, the server says, okay, because it got also the information, it got the pre-master secret, the server random, and the client random, it can generate all the keys as well. So both sides have all the same keys. So in this case, it can say, okay, well, I'm going to change my cipher spec protocol as well. I'm going to talk encrypted here as well. And again, the next message you're going to see is absolutely garbled because there's something in there, I just can't read it. But the client and the server can decrypt it. So we just did the change cipher spec on that side and the change cipher spec on that side. And this is where we actually are done. Because here's where we actually get to our HTTP level, because everything is done right now. And the next record is this, application data. What's inside? I have no idea. But it works. So this is where the HTTPS gets into action. If you're at that point, everything will be cool. Obviously, if you're going to debug stuff, it would be really nice to see, okay, it does something, but what's inside? Can I somehow figure it out? You can, because there are some web browsers that actually can give you information that allows Wireshark to encrypt that data for you. That's actually done with an environment setting called SSL key log file. If you're on a Mac and you just do this, so set the environment SSL key log file to something else, to a file, it will actually record all the pre-master secrets that you send out on HTTPS connections. And that information can be used by Wireshark to actually snoop inside your connection. And I can show you, because when I go to Wireshark, here I go to protocols, open it, go to SSL. They still name it SSL, I don't know why. And you type here the key name. I just used this key name before. I say okay. And what actually happens here is that I can see information. So I have my TLS record with application data that's encrypted, but Wireshark says, oh, but this is inside it. So I can actually snoop inside a connection. So this is really cool. And I showed you that after a change cipher spec, something happened. So there's another record going on, and I can actually see that record now. It's actually called a finished record. And that finished record has some information that proves that everything you just sent, I understand, because I can do something encrypted to you. So they can verify if both sides are on the same level. So it's really cool. You can figure out what's going on inside an HTTPS connection through Wireshark if you do it this. Your browser has to support it. I know Chrome support it. I don't know if others once support it as well. Obviously not IE, obviously not Saffire, but maybe Opera and everything. So you can figure out what's going on. Cool, huh?
Yeah.
Cool. At least somebody found it really cool. So TLS has got some overhead because you need something to do encrypt stuff, but it's definitely worth it. So definitely try and use it. I showed you before, some cipher suites are better than others. So like the RC4 cipher suite, don't use it unless you absolutely need it. There are stronger ones, but it's always a speed security trade-off. So maybe others are better, but obviously when you use that ones, you need more computation power on your server. So your servers will be more busy. So it depends on how high traffic your websites are. I can reckon that if you have a site like Tweakers, for instance, you don't want to use like the biggest and most expensive cipher because it takes too long to get an HTTPS connection up and running. So your servers will be, more used. So are we safe yet? We know how to make our ciphers okay. We know how to configure web servers. We can actually see. Are we safe? No, obviously, otherwise, if I say yes, then I will be done. So let's go back to that pre-master secret thing, right? That's the most important thing we have. If we can decrypt that pre-master secret somehow, we can deduce all the other information, all the client keys. So what if somebody, and with somebody I mean NSA, stuff like that, those people, what if they get hold of the site's private key? They can derive all the secrets, just like I did. Yeah? what happens is, and we just recently figured out that Pink Floyd, in this case, yeah, they're evil bastards, Pink Floyd. What they do is they store the communication, encrypted communication. They just store the data. They have no idea what's inside, they just store it. What they do is they just play the waiting game. They just wait until they figure out how to crack certain keys. They wait until they forced companies to get their keys one way or another way. And then they can crack all the data. But they can crack the data that we actually used a year ago because they store the data on their, I don't know, they have a big MySQL database. I don't know how they do it. Maybe. But this is why they can actually see, capture something today, and then in a year they figure out, this is what they did last year. They send over some message or some evil message. And sometimes it's really not important, but sometimes it can be really important. Obviously, we don't want that because obviously we don't do evil stuff, but rather not that somehow now or in the future our communication, private communication, will be unprivate. So this is where perfect forwarding secrecy comes in. And now somebody here in the room is like, yes, I wanted to know that. Anyone heard of this? Yeah, people get more to it. But perfect forwarding secrecy, or actually forwarding secrecy, is a way that if you compromise the pre-master secret, the first number, the most important number, it cannot compromise our communication. So we're still safe with our communication. You can't figure out what we're doing. It's too complex to tell you how it works, but this is pretty much what perfect forwarding secrecy does. You have something else called perfect forwarding secrecy, and that means that you can't compromise one key with other keys. Now, if you use this kind of ciphers, because there are some ciphers that are actually forwarding secrecy enabled, if you use those ciphers, then NSA can store whatever they want. This is on record right now, so I have to be careful. So they can store whatever they want, but they can't encrypt it or decrypt it in the future. They can't. They can't decrypt it real time. They can't decrypt it right now, at least not through this level. They have other ways of doing stuff like that, but at least the communication in this way is safe. So perfect forwarding secrecy is something you want to enable on your servers, right? Makes sense. Unfortunately, PFS needs server and browser support, just like SNI needs server and browser support. This is what's currently happening. If you are on Firefox, about 33% of all the SSL connections are perfect forwarding secrecy. All the rest are just NSA meat. Same if you are using Google Chrome, same if you use Opera. If you use Safari and you are really, really lucky, then you might have a chance. Otherwise, pretty much no. And if you're on Internet Explorer, you're doomed. Because Internet Explorer uses the ciphers that allows you to do forward secrecy. Nowadays, and I mean that just recently, just like the last half year, more and more browsers start to incorporate those ciphers, so you can actually use them more and more, but still it takes a long time to get rid of the browsers that don't support forwarding secrecy. If you look here, this is on Netcraft, and Netcraft, well, not really that long time ago. If you are on Nginx web servers, most Nginx web servers, if you connect with a Firefox browser, 78% of the time it's perfect forwarding secrecy enabled. If you go to any Microsoft website, and even if you use an Internet Explorer, okay. Pretty much all bets are off if you're using Microsoft products or if you use Apple products, Safari, and go to Apple websites. This is why I needed to use Microsoft.com to show you the communication, because the communication will be more complex if you go to GitHub.com or Google.com, because they're using perfect forwarding secrecy. If you update your cipher suite and you place your perfect forwarding secret ciphers at the top, then you're pretty much set. This is what I did in the 2 configurations I showed you before. They actually use pretty forwarding secrecy ciphers first. If you don't have them, we fall back to something else. So we still support all the browsers, but if you are capable of PFS, we actually use it. So that's really a great thing. If you go to the SSL Labs website I showed you before, that actually shows you, okay, on most browsers, your site is guarded through PFS, so hooray. So you can actually, figure out what's going on there. But you have to be aware, there will be heavy computations involved. So if you have high traffic websites, I understand if you don't use PFS. This is one of the reasons why Google and GitHub didn't use it before, but nowadays they use. So they said, okay, it's more important that we have better security than less load on our servers. So again, SSL test, this is a really cool website. Just type in your website and just laugh, and it's well fun. So I know it's a little bit more information, but I'm pretty much done. Unless you have a really good reason not to, you can just get your cheapest SSL certificates as possible. That's more than enough, unless you need extended validation or domain validation or stuff like that. There's a really cool thing called HTTP Strict Transport Security Header. You can add that to your website to send it out to the browsers. What it actually does on things like Chrome and Opera, I think, obviously Safari and IE not, when it sees that you are going to an HTTP, if you're on a website and you see, oh, that website starts with HTTP, but you already said there's a strict transport header security there already, then it will say, okay, I don't use HTTP, I automatically go to HTTPS. So it's a more of telling the browser, never going to use this website on HTTP, but always automatically go to HTTPS, which is really cool, but not every browser will support that right now. Don't support SSL 3 or older. 3 maybe if you have a really good reason. There's still some older browsers that might need it. Support PFS unless you have a really good reason not to. And check really through SSLlab.coms. There's also a best practices on that website as well to show you what you need to do to get the perfect HTTPS setup on that system for now, because in 6 months time, things will have changed again and you might need to change your configuration to be the best of the most secure as well. So update that as well. Okay, phew, that's it. Okay.
Awesome. Well,
yes.
Thank you very much.
All right, thanks.